Alright, welcome. In this video, I'm going to be working Algebra 2 Homework 7.3. But in this video, I'm only going to be working the problems that are talking about the complex conjugates theorem, and that's going to be numbers 1, 4, and 13 through 17. If you're looking for, the solutions to problems 2 or 3 or 5 through 12, those problems that deal with Descartes' rule of signs, that's going to be in a different video, and you can probably access that video, by clicking a link right about there, or waiting until the end of this video, and that one will be just the suggested next video. Okay, let's start with number 1. Alright, so number 1 says determine the number of imaginary zeros. Okay, if this is a degree 8 polynomial, and I can see two real zeros, and they're both single roots, that means I have 6 roots unaccounted for, and so I'm going to assume they're all imaginary. So that would be 6 imaginary roots. Yeah, and we see the arrows on the kind of the ends of that polynomial, so we know it's not going to be coming back and intersecting again. So we know it's 2 real and 6 imaginary. Okay. This next one's a degree 5 polynomial with 1 single root, which means that it's got to have 4 imaginary roots. I suppose that's really more the fundamental theorem of algebra than the theorem about complex conjugates, but I guess the thing that I would point out, because we're talking about that, is that complex roots always come in conjugate pairs, so we're always going to have an even number of them. Okay, this next one is asking about positive zeros. That's Descartes' rule of signs. We're going to save that to a different video. Alright, now we're going to write the fourth degree polynomial that has real coefficients and has zeros at x equals 2, x equals 3, and x equals 2i, and has a leading coefficient of 5. Okay, so what we know, we learned recently, is that if x equals, no wait, not 2, pardon me, 3, I was going to say 0 plus 2i is a root of a polynomial with real coefficients, then 0 minus 2i has to also be a root because of the complex conjugates theorem. So what I'm going to do is I'm going to set up for this polynomial like y equals some constant multiplied by x minus 2 multiplied by x minus 3 multiplied by x minus 2i multiplied by x minus negative 2i. And if we're saying the leading coefficient is 5, then that means that a is going to need to be 5. Okay, so it's going to be 5 times, maybe I'll distribute these two, so I'm kind of like unfactoring, so it's going to be the sum of the two numbers here, negative 2 plus negative 3 will be negative 5x, and the product is positive 6. And over here, this is going to be a difference of 2 squares. It'll be x squared minus, okay, if I take 2i and multiply it by 2i, I get 4i squared, so it's going to be minus negative 4, x squared plus 4. Okay. Can't be x squared minus 4 because we know that factors into x plus 2 and x minus 2 without the i's. Okay, now our job is going to be to distribute that. So I think I'll do that off to the side. X squared negative 5x and positive 6 multiplied by x squared and positive 4. Okay, looks good, I think. I'm just double checking. Okay, yeah, looks good to me. I made a mistake, I can't spot it, so I'm going to say, alright, this is going to be 5 times, and I'm going to just kind of look for my highest power term, that's x to the 4. And x to the 3's, I've got negative 5 of those. For x squareds, I've got positive 4 and positive 6, so that's 10. X's, I've got negative 20x and positive 24. Okay, and then I'll distribute the 5 across all of that, and I'll get 5x to the 4 minus 25x to the 3 plus 50x to the 2 minus 100x. Now 24 times 5 Okay, you could think of this two different ways. You could say 5 times 20 and 5 times 4. That'd be 120. Or you could remember that multiplying by 5 is a lot like dividing in half. So it's like divide in half and then add a 0. And so it's going to be 12, because that's half of 24, with a 0 on it. So that'd be 120 either way. And then maybe I'll just, whoops, you gotta get that out of here so I can just display my solution like that. Yeah, that's my polynomial. Oh, and I also want to point out that, it says, write your polynomial or your answer in standard form. That's where we're going to go all the way to here. Had it only asked for it in factored form, we could have just stopped, right there, but with probably 5 substituted in for A. All right, numbers 5 through 12 again are Descartes rule of signs problems, so I'm going to skip those and record those in a separate video. So I'm moving on to number 13 now. So what is the least number of zeros a polynomial with rational coefficients can have when 2 of them are root 5 and 3 minus I? Write the polynomial in standard form. Okay, so if we're rational coefficients, that also, like within rational, we mean real and rational. The rational numbers are a subset of the real numbers. That's kind of a subtlety that I don't think I pointed out in the lesson. So we've got zeros at root 5 and 3 minus I. Okay, so we learned in the last unit that if x equals positive root 5 is a root of a polynomial with rational coefficients, then x equals negative root 5 also has to be. So I'm going to kind of get a running tally of my roots. X equals root 5, x equals negative root 5. X equals 3 minus I, and the thing we learned about this time was that if x equals 3 minus I is a root, then x equals 3 plus I is going to need to be a root as well. Okay, and so now we're going to set up a factored form polynomial. And, oh, okay, but hold on, that would be at least, the least number of zeros, that would be 4. It could be the case that there are other zeros that they just didn't tell us about, right? But we're just going to assume the minimal polynomial here, and I'm also going to assume leading coefficient 1. So I'm going to set up, okay, y equals x minus square root 5, x minus negative square root 5, and then x minus 3 minus I, and x minus 3 plus I. Okay. Now, hopefully you've done enough of these where, you're starting to recognize the pattern here where this is going to turn into x squared minus 5. But if you haven't, just keep working. We'll do enough of these problems that it'll start to feel familiar. And this, this kind of product over here is something I'm thinking I'm going to need to do with a box. So x minus 3, and if I'm subtracting negative I, that'll be plus I, multiplied by x minus 3 and minus I, if I distribute that negative there. Okay, and then I'm going to fill out the box. I don't think you need me to narrate that. Okay, there we go. So notice that, the things with an I in them cancel off. And I squared is something that I can replace with negative 1, right? So I'm going to go in there and do that. So it's negative 1. And yeah, so now I'm going to have x squared, negative 6x, and positive 10. X squared, negative 6x, plus 10. All right, and then I think I'm going to need to do a little bit more multiplication. Yeah, let's just set up for that. And then maybe I'll do this multiplication in blue. I'll have x squared and a minus 5 multiplying by x squared, negative 6x, and positive 10. right? And there we go. And I'm just going to kind of combine like terms, and I'll have my polynomial. I'll have x to the 4 minus 6x cubed plus 5x squared. I'm going to add the positive 10 and the negative 5 plus 30x's and minus 50. Okay, that would be my standard form polynomial. Hey, they'd asked for it in factored form. That would have been right here. All right, the next one's kind of what's possible and what's not possible. Okay, so suppose P is a 4-3 polynomial that has rational coefficients, and by rational we mean real coefficients, and we've got two imaginary roots, and x equals root 2 is a root of P. Well, okay, from the fundamental theorem of algebra, we know that if there's a 4-3 polynomial, there's 4 total roots up to, multiplicity and complex roots, or imaginary roots. So I've got two imaginary roots. So I'm going to say that means I've got x equals a plus bi and x equals a minus bi. We don't really know what a and b are, but we know that there are two imaginary roots, and we also know that they're going to be conjugates. Okay, we've got x equals 2 is also a root. So there's this fourth root that we don't know what it is. But I can tell for sure that it's got to be real because there's not enough room for us to have two more roots, which is what we would need if we were going to have any more imaginaries, right? So we need room for its friend, its conjugate pair. Okay, and kind of the same thing with square root 6. Okay, x equals square root 6 is not going to be a possible root because if it was, and we had rational coefficients, we would also need x equals the negative square root of 6. So I think I'm just going to write in my explanation. Alright, so this is going to be my explanation, and this is kind of getting on the way to something like proof by contradiction. So I'm going to say no because, we know from the fundamental theorem of algebra that there are 4 total roots based on the degree. And if we did have x equals square root 6 as a root, then we'd also have x equals negative square root of 6 because of the rational coefficients thing. But then there would be 5 roots, okay, and that would be like kind of breaking the rule that I know is true. So I'm going to say no. Okay, if P didn't necessarily have rational coefficients, would it be possible for P to have roots, okay, x equals 0, I, negative I, and root 6? Oh yeah, totally. Fourth degree, those 4 roots, I'm going to write an equation that could represent P. So let's say P of x equals some number times x minus 0 times x minus I times x minus negative I, and x minus the square root of 6. Okay, that's an equation. Okay, maybe I make a choice of a, and maybe I decide a is going to be 1. Okay, that's an equation that could represent P if P had a leading coefficient of 1. It's just not going to have rational coefficients. This is in factored form, but it didn't say a standard form equation that could represent P. It just said any old equation that could represent P. So I think that's what I'm just going to leave it right there. Right, now these last two, these are kind of like the classical minimal polynomial problem. And so I think, yeah, this will be a good couple of problems for us to wrap up our practice with. So a double rooted x equals 0 means I'm going to have the factor x minus 0 twice. So x minus 0 times x minus 0. And a single rooted x equals 2 plus I. Now, if we're going to have rational coefficients, that means that x equals 2 minus I needs to also be a root. And I'm going to start to, simplify things and distribute. Okay, first of all, if they're saying the leading coefficient is 1, that means a needs to be 1. So just put that in there. Okay, x minus 0 times x minus 0, that's just going to be x squared. And then I'm going to kind of distribute these negatives. X minus 2 minus I multiplied by x minus 2 plus I. And I'm going to get to multiplying. So I'm going to kind of go off to the side and make a box. But I'm thinking but that's going to kind of be it. So I need to be super careful about space. X minus 2 minus I multiplied by x minus 2 and plus an I. Okay, there we go, and we're going to have things with, wait, that would go there, and this one would go there. I've lost a term, but that was negative 2x. And, all right, I can combine my like terms, and remember that I squared is negative 1. Oops. So it was negative 1. I'm going to have x squared minus 4x plus 5 times x squared minus 4x plus 5. And then I'm going to distribute, and I'll get x to the 4 minus 4x to the third plus 5x squared. All right, now the last problem we've got is, oh wow, a lot of double roots. Okay, so if we got a double root at x equals 1, and a double root at x equals negative 1, and a double root at x equals I, that means we gotta have a double root at x equals negative I as well, so it's gonna be an 8th degree polynomial. So this might sound scary, but I can see what's gonna happen here. If we are kind of strategic about how we multiply this out, it's gonna work out just fine. So, I'm gonna have, oh, hold on. I'm gonna add in my own bullet point that I've got a double root at x equals negative I. Okay. And I'm going to say what I'm going to say here. Okay, set up my factors, I guess. Y is equal to a leading coefficient times x minus 1 squared times x minus negative 1 squared, and I'm not going to be squaring all of these out. I'll tell you that right now. X equals I is a double root, so x minus I squared, and double rooted x equals negative I squared. Okay, so wait, no, I guess double root x equals negative I. That gives me x plus I squared. Okay, so what I'm going to do is I'm going to remember that, you know, like if I have x minus 1 and x plus 1 and I multiply those together, it ends up giving me a difference of 2 squares. And the same thing could happen with x minus I and x plus I. And I've got all this stuff squared. So what I'm going to do is I'm going to, well, I guess, start with leading coefficient and make that replacement. So negative 2. And then I'm going to say, all right, well, I've got x minus 1, x plus 1, x minus I, and x plus I, all of this squared, right? Because I got 2 of each of them. And then I'm going to say, okay, I'm going to maybe take them 2 at a time. X minus 1 times x plus 1, that's going to be x squared minus 1, right? Because it would be x squared plus x minus 1. And then I made a copy error here. Yeah, let's see, so it's going to be x minus I and x plus I, pardon me. And then, yeah, x minus I times x plus I will be x squared plus ix minus an I squared, so minus negative 1. Okay, and we're still squaring this. But I think I'm going to hold off for a little longer before squaring this, right? Because I could probably multiply these two things, right? And that's going to give me another difference of 2 squares. So still got that negative 2 on the outside. But then when I go to do kind of FOIL here on the first 2, I'll have x to the 4. The outside 2, I'll have positive x squared. The inside 2, I'll have negative x squared. So the last 2 would be negative 1. And now I'm still squaring this. I've only been simplifying the inside of the thing in square brackets this whole time, right? So now I'm going to have to, multiply that out. So negative 2 times x to the 4 minus 1 times x to the 4 minus 1. And I'm going to have, okay, negative 2 times, okay, I'm going to do FOIL one more time. Let's FOIL here. X to the 8 minus an x to the 4 minus another x to the 4 will be minus 2x to the 4s. And the last 2 plus 1. So then my polynomial is negative 2x to the 8 plus 4x to the 4 minus 2. Okay. So yeah, that one was a lot, but you know, if we approached it strategically, we were really able to, you know, lessen the work on ourselves. Oh, and I guess, yeah, that's all the problems we've got for this video, so that's going to be it. Thanks for watching.